But is my voice okay? I'm from a distance from the mic.
Good afternoon once again and welcome back to today's first paper presentation session. This session focuses on public key encryption and protocols. For this session, we have the two session chairs with us, Professor Sharman S.M. Chow and Professor Rana Barua. So over to you, to the session chair. Thank you.
Hi. Sharman, you please take over because most of the presentations are online.
Oh, okay, thanks. I will do that. So we have very interesting talk today, and we will start with something about ID-based matchmaking encryption, and the talk will be given by Luigi, if I pronounce your name correctly. So I would like him to introduce his co-author. So the floor is yours. Thank you.
Hi everyone, my name is Luigi Russo, and today I'm going to present you this paper entitled Identity-Based Matchmaking Encryption Without Random Oracles. This paper has been written with Danilo Francati at Aarhus University, Alessio Guidi and Daniele Venturi of Sapienza University of Rome. Sorry.
Luigi, sorry to interrupt. Can we have your video on, please?
Yeah, sorry. Can you see me?
Yes.
Yes, thank you.
Yeah, sorry. Okay, so before going to details of the paper, I will start with a brief introduction about the topic. Identity-based encryption is a type of public key encryption introduced by Adi Shamir in 1984. In this context, users do not require public keys, but the public keys are just some identifying information, for example, email addresses. So in this figure, we can see that Alice, in a classical scenario, wants to send a message to Bob. She doesn't have to retrieve his public key, but can just use his email address as public key. IBE is a powerful primitive that has been widely studied, and there are a lot of applications. Among them, I just recall some of them. For example, the revocation of public keys, the delegation of decryption keys, the authentication, and many, many more. Among the flavors of IBE, a very important one is the so-called anonymous identity-based encryption. In particular, this captures the following scenario. Given a ciphertext, no adversary should be able to distinguish the target identity from a random one. So, for example, Alice encrypts a message to Bob, and no adversary should be able to understand that the ciphertext is really directed to Bob rather than, say, Charlie, so another user in the system. Identity-based matchmaking encryption instead is a novel primitive introduced at Crypto 19 by Ateniese, Francati, Nunez, and Venturi. In this context, we have that the two parties, so both the sender and the receiver, can specify a target identity. So the sender can specify the receiver identity, as in the normal case, but also the receiver can specify the sender identity. So when both target identities match, so we say that a match occurs, the decryption is successful, so the receiver can retrieve the plaintext. Otherwise, we want that no information has to be leaked. In particular, the sender's identity, the target identity, and the plaintext have to remain hidden. Identity-based matchmaking encryption is a special case of matchmaking encryption, which allows parties to send messages specifying arbitrary policies. So this is the syntax. We have a setup algorithm that generates the master keys, the master public and the master secret one. We have three algorithms for the keys. The sender key gen that takes in input the attributes of the sender and generates the keys associated with these attributes. We have the RKGen that does the same, but for the receiver side. And we have this PolGen algorithm that takes in input an arbitrary function, an arbitrary policy phi, and generates a key associated with this policy. We then have the two classical algorithms, encrypt and decrypt, where the encryption algorithm takes in input an encryption key associated with the attributes of the sender, a general policy R that must be satisfied at the receiver side, and the plaintext. And finally, we have the decrypt algorithm that takes in input the decryption key associated with the attributes of the receiver, a decryption key generated with the PolGen algorithm associated with a policy S that the sender has to satisfy, and finally the ciphertext. In the identity-based context, instead, the encryption and decryption algorithm takes in input directly the identities, so the target identity rho and the target identity sigma. So there is no need to implement this PolGen algorithm, because otherwise the performance would degrade, in the sense that we would have too many, basically one key for each sender, and so this is not acceptable anymore. Also, identity-based matchmaking encryption has a lot of applications. In particular, it finds applications in all those settings where an IBE with strong anonymity guarantees are required. For example, the authors of the original paper have implemented a privacy-preserving bulletin board over Tor, using Tor hidden services. And this can be used, say, by newspapers to collect information from anonymous sources. So anyone can encrypt a message, can specify a policy, can publish it on the bulletin board, and anyone can try to decrypt, specifying clearly a standard policy. So we now move to the main contributions of this paper. And there are two main results that we have achieved. The first one is that we have given a stronger and more meaningful security definitions in the context of IBME compared to the original paper. And the second one is that we have constructed the first IBM scheme without random oracles. So we have to define what is privacy in this context. So privacy, as defined in the original paper, is defined through an indistinguishability game, where an adversary has to commit to two messages, two target receiver identities, two sender identities, and then the challenger samples at random a bit B and generates samples a key associated with the attributes sigma B, and gives the adversary a ciphertext that is just an encryption of the plaintext MB. Then the adversary has to tell apart the two experiments. The problem is that this privacy game offers no guarantee when the receiver's identity matches the target identity specified by the sender. Because we somehow have to restrict the class of the adversaries. So we define a class of valid adversaries. And the problem is that since the receiver can choose sender's identities on the fly during the decryption process, the authors of Crypto 19 paper have not considered adversaries who do not hold a decryption key for the target identities. And this, for example, implies that we can build some very strange schemes, for example, the following one, that satisfy the privacy, the privacy as defined by them. So take any anonymous IB scheme, encrypt as a plaintext the plaintext concatenated with the sender attributes, and then what the receiver can do is just to decrypt and see if a match occurs between his policy and the sigma. But then he is always able to retrieve the plaintext and sigma, so this somehow breaks the security, even though the security seems to be guaranteed. So how is that being defined? So this suggested us to move to upgrade the privacy definition to the so-called enhanced privacy. In this context, the sender's identities remain hidden, even when the adversary holds a decryption key for the target identity. So we have redefined the game, we have modified it. Now the adversary has to commit to sender distributions, these are ID 0 and ID 1, rather than to sender's identities. And now we allow the challenger to sample from this distribution. So we allow an adversary to hold the decryption key for a target identity, but there is a constraint that these distributions have to have some high mean entropy. So the previous scheme, the contrib one, is not secure anymore under this enhanced privacy property, because we can just use an adversary that samples two ID0 and ID1 with a high mean entropy, but whose intersection is empty. So once, if it owns a decryption key for the target identity, it retrieves the sigma attributes, and then it's easy to distinguish the two experiments. I briefly introduced what is a reusable computational extractor, because this is used in our construction. A computational extractor is a polynomial time algorithm that takes in input a public random seed S, a value X that has to be sampled from a distribution with high mean entropy, and it outputs a value Y that is pseudo-random. A reusable computational extractor is a computational extractor that can be safely evaluated multiple times on the same input. And we used it in our construction that is built on top of the anonymous IBE of Gentry, 2006. So we start from this anonymous IBE scheme. We add a second layer of encryption using a sort of one-time pad. And the randomness of this one-time pad is derived via a randomness extractor, where we publicly we publish the seed X. This is attached to the ciphertext, and we extract using this seed from the sigma, that is the attribute, the sender identity specified at the decryption time. This construction achieves our stronger notion of security, which, by the way, implies the previous one. So this is private. And so very briefly, how the decryption works. The first layer of encryption is removed, and this is done relying on the anonymous IB of Gentry, and then you just remove the second layer of encryption if you make the right guess for the sigma. And that's all. So thank you for your attention. Here there is just a brief list of references that I've used in the slides.
Thank you.
Thank you.
Thank you.
Are there any questions from the audience? Yeah? Yeah, okay. I have a query. Instead of, have you ever thought of attribute-based matchmaking encryption? Because you talk about policy. So instead of identity-based matchmaking encryption, have you thought of attribute-based encryption?
Not in this paper, but in the Crypto 19 paper, matchmaking encryption for arbitrary policies, for arbitrary users, I would say, is also managed, is also handled. So in the matchmaking encryption captures is a generalization of attribute-based encryption. So, but in this paper, we didn't address the general case.
Okay. So any online question, Sherman?
Maybe I ask a follow-up. So first of all, I apologize for pronouncing your name back. And so I understand from that crypto paper, it's still used relatively heavily, primitive, right? So that maybe your trade secret, but have you start to thought of how to do a weaker version of policy, but using weaker primitive? Anything you want to share?
Sorry, I didn't.
Basically means without using functional encryption, have you thought of how do you still achieve some meaningful policy beyond equality?
You mean for arbitrary policies?
Yeah. But not all the way arbitrary, but maybe some weaker one, but somehow you can manage to use such payment maybe.
Okay, so for arbitrary policies, clearly we use the functional encryption, or well, randomized functional encryption. So it's even a stronger notion of functional encryption, because the authors have proved that this functional encryption somehow seems to not be sufficient to construct matchmaking encryption for arbitrary policies, because there are two policies that have to be matched at the same time. Okay. We have considered the easiest case, we can say, that is the equality policy. So identity-based matchmaking encryption is just considering the equality policy. For the intermediate case, we didn't address that, but it would be interesting, I think, to see what we can achieve. Yeah.
Yeah, I think so. Thank you. I'm also very interested. Sorry, we essentially used up the time, but we do have another Q&A room after the talk, right? So yeah, please stay tuned and just let us know if you have further questions. Hope to see you in the Q&A room. Otherwise, thank you.
Thank you.
Yes.
Okay, thank you so much. And we will have the second paper also about public key encryption, but about something also different, how to achieve voice security without key update. Okay, and we have Shanya Lutasan, who will present their work. So the floor is yours.
Okay, thank you for the introduction. I'm Seiya Nuta, and I will talk about false key public key encryption without key update from proof of stake blockchain. This is a joint work with Jakob Schult and Takashi Nishite. So here is an overview of my talk. First, a false security is a security notion that guarantees even if an adversary gets a secret key, they cannot decrypt past ciphertext using the secret key. And in prior works, in non-interactive setting like public key encryption, false security has been achieved by updating the secret key. So our contribution is to present the first construction of a false secure PKE without key update, assuming proof of stake based blockchain access. And using blockchain in PKEs is unusual, but it gives us some interesting properties in addition to false security. I will talk about interesting properties at the end of my talk. So its core idea is to make our ciphertext decryptable only once by using proof of stake based blockchain as an immutable bulletin board to determine if a ciphertext has already been decrypted. So first, I will talk about background. So in public key encryption, the sender Bob encrypts a message using the receiver I's public key, and then receiver I's decrypts the ciphertext using her secret key. And even if an adversary Eve get a ciphertext, they cannot learn anything about the message. But it is quite clear that if Eve gets the secret key, they can easily decrypt the ciphertext. So in false secure PKE, we add a new algorithm called update. So in false secure PKE, ICE periodically updates her secret key using the previous secret key. And even if an adversary Eve gets the current secret key, she cannot decrypt past ciphertext because she don't have a previous secret keys, and because they are updated and dated in past. So in a non-interactive setting like a PK scheme, false security has been achieved by key updates, like in a non-interactive key exchange, zero RTT key exchange, and puncturable encryption, for example. So question here is it possible to achieve false security without key update? And achieving false security without key updates provides some good benefits. For example, in our construction, the size of the secret key become constant, while in prior works, they are depend on number of key updates. So in our paper, we present the first construction of a for secure PKE without key update. And the idea is to make a ciphertext decryptable only once using blockchain. So next, I talk about some building blocks for our construction. First one is witness encryption. Witness encryption uses NP language, and instead of using key pair like public key encryption, in witness encryption, we use NP statement to encrypt a message and the corresponding witness to decrypt a ciphertext. So in witness encryption, we don't have key generation algorithms, and instead it takes X NP statement to encrypt a message, and to decrypt the ciphertext, it takes corresponding witness to ZX. So next building block is a blockchain protocol. A blockchain protocol is a protocol which aims to maintain a chain of blocks, and it introduces consensus algorithm like proof of work and proof of stake to maintain the chain of blocks without trusted third party. Here I give you abstracted model of blockchain protocol from Goyal and Goyal's paper. In this abstracted model, we have three algorithms. The first one is update state, which communicate with the blockchain network to keep the local machine synchronized. The second algorithm get records output the blocks in the blockchain. And lastly, broadcast algorithm takes a message and it writes the message into the blockchain. So one of consensus algorithm in blockchain called proof of stake. In that consensus algorithm, we can assume a following fact. If we assume that adversary has only a few stakes compared to all other honest parties, we can say that adversary cannot create a sufficiently long fork of honest blockchain, because at first in the adversary's fork, they can use their own stake to prove their stakes, but eventually they need to forge or generate valid stake, even if despite they don't have sufficient stake to prove the last block. And in Goyal's paper, they showed that on some proof of stake based blockchain protocols, assuming that adversary have only limited fraction of stake, an honestly created sufficiently long blockchain is distinguishable from adversary's fork. And this property called distinguishable forking property is used in our construction. So next I talk about construction. So a forward secure public key encryption scheme without key update, which is our construction, is consisted by following three algorithms: key generation, encryption, and decryption. And as you can see, it is looks like a usual PK scheme, because we no longer have to add some additional algorithm like key update. So And in our construction, the core idea is to allow decrypting a ciphertext only once by checking decryption attempts in the blockchain. So this means that if adversary Eve obtains the Alice's secret key, it cannot decrypt a past ciphertext because they are already decrypted by Alice, and the decryption are recorded on the blockchain, and thus it achieves the full security. So here is how to implement the one-time decryption. In our construction, we require the first decryption attempt to decrypt a message, a ciphertext. So in this diagram, first Alice received ciphertext and decrypts using the decryption algorithm. And after that, if Eve gets the same secret key, but she cannot use the secret key to decrypt a ciphertext because it is already decrypted by Alice and it's recorded on blockchain. And to decrypt the ciphertext, Eve needs to fork blockchain from before the Alice's record, and creating a sufficiently long blockchain is hard because of distinguishable forking property, which I described before. So let's look into each algorithm. First key generation algorithm is pretty simple because it just generates digital signature schemes key pair and output as they are. So next, in encryption algorithm, first we download the latest blocks from the blockchain, generate a unique message ID, and encrypt using witness encryption. And NP relation used in our construction will be described later. So lastly, the decryption algorithm is a bit complicated. So first, what we do is create an ephemeral secret. And then we sign the ephemeral secret using the long-term secret key and write the signature into the blockchain. After that, we need to wait for a while until the blockchain sufficient growth to satisfy the distinguishable forking property. And then we download the latest blocks from the blockchain. So lastly, we give the latest blockchain and ephemeral secret to decryption algorithm. And then we delete ephemeral secret because it is necessary to prevent adversary to use the ephemeral secret after, and then output the decrypted message. So here is NP relation used in our construction. Because it's a bit complicated, so I will give you an overview of the relationship. So in the relation, we check three facts. First, the ciphertext has not yet been decrypted, so we ensure that the decryption is the first one. Next, decryptor knows that the ephemeral secret ESK, so that even if adversary gets the secret key and tries to decrypt the message, she cannot decrypt the past ciphertext because she don't know about the ephemeral secret. And lastly, we check that the given blockchain is not generated by adversary, and we can check it using thanks to distinguishable forking property presented by Goyal and Goyal. And the detail of the construction can be found in our paper. So next is discussion. So in addition to for security, our construction has some interesting properties. First is constant key size, because we use digital signature schemes and key pair as our construction's key pair. The size is constant despite previous works depend on the number of key updates. And next one is key leakage detection. Because adversary need to post a valid record into the honest blockchain. So ICE can monitor the blockchain, and if she detect valid record for her secret key, it is a sign of key leakage. And finally, lastly, post-compromise security, because even adversary get the secret key, she needed to decrypt ciphertext before Alice does. So adversary needed to keep decrypting actively. So here is open problems of our construction. First is efficiency. Because our construction requires blockchain access, and we use a complicated relation in witness encryption. So this is why our work is still in feasibility result, and it's not yet practical. And another problem is privacy concern. We can notice key leakage, but since ICE need to post a record into the blockchain, anyone monitoring the blockchain will be able to tell when ICE decrypts a ciphertext. So it's like a privacy concern. So here is my overview of my presentation. Thank you.
Okay, are there any questions offline? Any? Okay, then. Okay, I just have a curiosity. You said that the ciphertext can be decrypted only once, right? Isn't that a very strong condition, restriction?
Yes. Because in ordinary public key encryption, we can decrypt a ciphertext many times, but in our scheme, we can decrypt it only once.
Only once.
Yeah,
so that seems to be a.
Yeah.
You try to remove this restriction, no?
Yeah, but if I allow decrypting several times, it breaks for security, because if the ciphertext can be decrypted many times, it means that secret key can be used to decrypt past ciphertext.
Okay, thank you. Yeah, Sharmin.
Thank you. I didn't see any question yet. David, just feel free to unmute yourself if you want to ask a question. Maybe we want to ask one interesting work, new idea. And so I'm also wondering if there's maybe a random question. So there's another notion called punchable encryption, which also try to address this kind of situation, but maybe by updating the ciphertext. So can it be helpful? Can this kind of technique you propose may be helpful to propose something new about another notion?
Sorry, I couldn't catch that.
Oh, okay. I'm wondering there is another notion called punchable encryption.
Yeah.
Which update the ciphertext, if I understood correctly.
No, it updates secret key.
Both. It punches part of the secret key. So that's also about key update. So I'm wondering if there can be any implication of your technique to this part.
So you mean there are any relationship with puncturable encryption and between that and our construction, right?
Yeah.
In our construction, we don't use puncturable encryption, obviously, and the difference is that in our scheme, we don't use key updates to achieve for security, and the same thing with puncturable encryption is that their puncturable encryption and our construction both implement fine-grained for security. So after decrypting a ciphertext and after updating the key, the past ciphertext become immediately undecryptable using the new updated key.
Thank you. Yeah, I understand the relationship may be too far away. It's a far-fetched question. Thank you. Any questions from the audience? Now we do have time. Let me double check whether we have Q&A waiting.
Okay, so let us thank
Yeah, I guess
the
so.
speaker again.
Yeah, thank you so much. We always have the Q&A session later. Okay, thank you.
Thank you.
Okay, and we now have the last one. So that's a bit difference is in a tab paper, which try to analyze an existing privacy preserving wide-hailing surface called Trace protocol. And we have the speaker, Pat, if I pronounce your name correctly. So yeah, the floor is yours. Thank you.
Yeah, thank you for the introduction. So this is a joint work with Dr. Srinivas Vivek. In this work, we propose an attack against the ride-hailing service Trace, and mainly we focus on the privacy claims made therein. So first, let us look at some examples of ride-hailing services. In recent years, to give you some statistics, Uber trips have increased from 140 million in 2016 to 6.9 billion in 2020. And so these services are becoming increasingly popular day by day. And the main features of this service are that they provide ride requests at the simple touch of a button. They also provide other features such as fare estimation and reputation ratings, including automatic payments. However, there are several privacy issues when it comes to ride-hailing services. They collect vast amount of information about riders and drivers. In particular, they keep track of pickup and drop locations, time of travel, etc. And there have been several news reports which indicate these violations of privacy. For example, Lyft was sued for violating the California privacy law. Uber employees used their app to spy on politicians and celebrities. Uber were tracking its drivers and they threatened to fire anyone who were attending taxi protests. So there have been several lines of works whose focus is particularly to ensure privacy in ride-hailing services. So Trace is one such protocol. It was a privacy-preserving solution proposed by Wang et al. At IEEE Transactions on Vehicular Technology 2018. The main contribution of this paper is that they hide the locations and identities of riders and drivers from the service provider during ride matching. In addition to this, they ensure efficient and accurate ride matching for riders and drivers in a region. So the three main entities in any ride-hailing service are the ride-hailing server who provides the service, the customers or the riders, and the vehicles or the drivers. So now I'll give a brief overview of Trace. So at the start, the server divides the two-dimensional space into several quadrants. So if you see this figure, N1 is the primary quadrant and it is divided into sub-quadrants N2, N3, N4, N5. N4 is further divided into N6 up to N9. And this is stored in the form of a secret quadtree N. Each quadrant is characterized by the four vertices that surround it. So the server computes the masked quadtree En of this data structure and sends it to the riders and drivers. RCs and RVs use this encrypted quadtree to mask their secret coordinates and they send it back to the server. Now the server who has the masked coordinates of riders and drivers finds the list of drivers who are in the same quadrant as RC. So this is done to ensure load balancing on the server and to minimize the number of requests that the server receives. So with this list of drivers who are in the same quadrant as the rider, the server computes the Euclidean distance between the rider and the drivers in that region and appropriately chooses the closest driver. And in this way, efficient and accurate right matching is also ensured. So the masking that is used in this process is through random secret integers, modulo public primes, and all these masked values are exchanged between entities using a public key encryption scheme. So our contribution is that Trace makes the following claims. So given the masked quad tree from the server, the riders and drivers do not learn anything about the underlying quad tree N. And the second claim is that the server can only learn the quadrants in which the riders and drivers lie and nothing more about their exact locations. So we propose efficient attacks. So first attack shows that the riders and drivers can indeed obtain the secret quad tree N that is maintained by the server. And this quad tree represents a spatial division of the region and may leak statistics about the distribution of driver density. To give you more context, smaller quadrants are chosen where the density of drivers is high to ensure minimal load on the server. The second attack shows that the server can recover the exact locations of all RCs and RVs in the region, and this is a clear breach of privacy. We also provide public implementation of these attacks for the security parameters that are recommended in TACE, and we show a very high success probability of recovery. So to give you a brief overview of our attacks, in the trace protocol, when masking is done for different messages, the protocol uses common randomness across different messages. And the reason they do this is so that the arithmetic is correct and that the Euclidean distance and the closest drivers are computed correctly. For example, when the server receives the masked information of locations from riders and drivers, there are several expressions where these common randomness are cancelled and the drivers within the quadrant of the rider are obtained. And so we make use of this common randomness, and we observe that they can be eliminated if we consider different messages that are sent by entities. Subsequently, when these unknown common randomness are eliminated, we are left with a system of linear modular equations only in the unknown plaintext locations. And the plaintext in case of the first attack is the quad tree N that is maintained by the server. In case of second attack, these plaintexts are the locations of riders and drivers, which the server intends to know. More importantly, our attack is efficient and it runs in time quadratic in the security parameters. And it is also purely algebraic in the sense that we make no assumptions about the geometry of the two-dimensional space. So the first attack is where the riders and drivers recover the secret quad tree maintained by the server. So we know that they receive a masked quad tree En, and if the quad tree has M nodes, N1 to Ni, the riders and drivers receive the masked quadrants En1 up to Enm. So each quadrant is composed of 4 vertices. Let's say the jth coordinate of the ith quadrant is denoted by Enij. The server computes 6 masked values as shown in the first 6 equations. In these, S and AJH are known only to the server, and Xnij and Ynij denote the quadrant, the jth vertex of the ith quadrant. And with these equations, the first step is that the riders and drivers eliminate the unknown randomness AJH, and this can be done by subtracting every pair of equations. Now, S is also unknown to the riders and drivers, and these also can be eliminated in many ways. One such example is shown in the last 3 equations. So finally, since the riders and drivers know all the Enijh masked values, they are left with a linear equation modulo P, where the only unknowns are Xnij and Ynij, which are the underlying coordinates of the quadrant, the masked tree, or the quad tree N. So in this way, in this example, we consider 2 quadrants, En1 and En2. And so if you consider them, we obtain a system of 28 linear equations in just 16 variables. And 16 variables because we have 2 quadrants with 4 vertices each, and each vertex is characterized by an XY pair. So, however, we experimentally observed that the rank of such a system was 13, and therefore we couldn't obtain unique solutions. This was simply resolved by considering simultaneous equations for 4 quadrants at a time, En1 up to En4. In this case, we obtained a system of 168 equations and 32 unknowns, and the rank of the system was also 32. And we used Gaussian elimination to obtain the unique values of the coordinates of quadtree n modulo p. So the second attack is where the server recovers the locations of riders and drivers, and this is a more impactful attack compared to the prior one, since this violates the privacy of rider and driver locations. So when the riders and drivers are given the masked quadtree En, they use it to mask their own locations. So suppose XV and YV are the locations of a rider, they mask it with respect to En as shown in these equations. So Rij is a random value integer that is chosen by the rider and unknown to the server. And alpha is a public value. And for each vertex, j equals 1 up to 4, the rider computes Aij. And to mask the order of vertices, the rider chooses a random secret permutation pi and permutes the Aij values and finally outputs A. AI is sent to the server. However, notice that this permutation is over 4 elements, and therefore the server can make guesses row. So if you permute AI and get a candidate AI dash, which is permuted according to row, assume for now that by chance the server ended up on the correct permutation, that is row is pi inverse. So this means that AI1 dash is the same as AI1, AI2 dash is same as AI2, which was originally computed by the rider. And here the server does not know Rij, and that can be easily eliminated from these two equations. And the server obtains a linear equation in XV and YV. So this can be done for j equals 1 to 4, and this means that the server obtains 4 linear equations in the two unknowns xv and yv. And the server solves these equations, and if the system is consistent, then with high probability the server can conclude that rho is pi inverse, and that xv yv that is obtained is indeed the exact location of rc and rv. And we said that the quadtree is composed of several nodes, and so the success probability of our attack can be exponentially increased by obtaining xv, yv for each I and finding the common intersection of these solutions. And with high probability, we indeed observed that the xv, yv corresponded to the actual location of the riders or drivers. So we provide experimental evaluation of our attacks for the security parameters that are recommended in trace. The first table shows the average time taken for the first attack where the riders and drivers recover the secret quadtree maintained by the server. We chose different sizes of quadtrees from 50 to 100. And we also conduct experiments for higher security parameters than what is recommended in trace. And we observed that these attacks are indeed feasible. The second table shows the attack, the timings for the attack where the server recovers exact locations of riders and drivers. And even in this case, the attack is very much feasible in practice. So in the recent years, there have been several works in the area of privacy preserving ride hailing services. While we saw that trace uses random masking, there are other works, for example, ORide, which uses homomorphic encryption, or PRide, which uses garbled circuits. But our attack is very much specific to trace because it uses random masking, and we use a system of linear equations to obtain the unknowns. However, it is not clear how our attack can be prevented. More importantly, the second attack where the server recovers the exact locations of RCs and RVs, we are not yet sure how to prevent it. However, the first attack where the servers recover the exact quadtree maintained by the server, this can be thwarted by carefully modifying the trace protocol, and the privacy claims for this countermeasure can be proved by using arguments similar to one-time pad. And I would recommend to see our paper for more details. But for future work, it would be interesting to see how a countermeasure can be proposed for the second attack in our paper. Thank you.
Any question from the audience? No. Any question online? I don't see. You are not audible, Sherman.
Yeah, thank you. Sorry about that. Maybe I start with one question. So thanks for the talk. And you mentioned about trying to fix the scheme, but if I understood correctly, if that's about solving linear system of equation, then you cannot really fix it, right? I mean, it's inherently you can invert the matrix if I understood correctly.
So our attack relies on solving a system of equations. You are correct. But it also relies on the fact that there are common randomness used when masking different equations. So when computing the different E and Ij values, the 6 values for each vertex in the secret quadri, there is common randomness used across, and this is done to ensure correctness of the protocol, where in a later point of time, these randomness get cancelled out and the server obtains the correct expression. If you decide to not use common randomness and use a unique randomness each time, this violates the correctness of the trace protocol and affects the right matching accuracy. So it is not clear how you can ensure correctness of the protocol while at the same time ensuring privacy as well.
Yeah, exactly. So if you just use different randomness, then you can really compute things unless you upgrade to HE, I suppose. And unless you use other things like homomorphic encryption, I guess you cannot really fix this approach, right?
Yes, that is how it seems.
Let me check. Thanks for answering my question. So let me check if there's any other question waiting for us. Maybe I also mentioned actually I noticed you have a ongoing work about also investigating the OY proposal from user security. Can you share something with us?
So there, so in that case, the Euclidean distance is used again as a sorting metric. So the attack there is that given the Euclidean distance, ideally there would be an infinite number of possible locations for the driver defined by the circle with that radius. However, they use homomorphic encryption and therefore the coordinates are encoded as integers. So if you use a system such as UTM, which maps floating point coordinates to integers, we actually end up with a very few number of lattice points on the circle. And so the number of possible locations are very less and not very large.
Okay, I see. Thank you. So
okay, let's thank the speaker again.
Okay, thank you.
Thank you.
Okay, so yeah, as mentioned repeatedly, we have a Q&A session online, so please join the Q&A session if you want a more intensive discussion. Okay, thank you.
Yeah, thank you.
So thank you, everyone. Thank you, Professor Sharman and Professor Borua for chairing this session. You can directly join to the author for QA session.